Our next category of sedimentary rocks are the chemical and biochemical sedimentary rocks. Chemical sedimentary rocks are not made of sediments. They're from elements and they're ions that are dissolved in water. There's hardly any pure water in the natural environment. It's always got minerals and other things dissolved in it. And these rocks have a crystalline texture where the crystals have interlocked with each other. Then there are the biochemical sedimentary rocks, and notice the difference here. The chemical sedimentary rocks are precipitated directly from the elements and ions in the water. Bio means that there's some life action involved in them. So from the actions of organisms or altered organic material in the example of coal, which is formed from plant material. They have a clastic texture sometimes. For example, if you have fragmented seashells that have been lithified, that is called fossiliferous limestone. So here's a table showing the classification of chemical and biochemical. Texture will vary with calcite. It can be crystalline to microcrystalline. Dolomite, gypsum is crystalline, and we know that halite or rock salt is crystalline. Calcite shells, that would be clastic, and altered microscopic shells, usually crystalline because they've been recrystallized in microcrystals, so you hardly see the crystals at all. And chert, or you might know that better as flint, is an example of that. And then we've got coal, which doesn't really have a texture at all, and that's carbon from altered plant material. So carbonate rocks will contain the carbonate radical, CO3. Limestone is made mainly from calcite. Dolostone is formed when limestone has had, buried limestone has had water moving through, and that water contains magnesium. And some of the calcite gets replaced with magnesium, and that is no longer limestone, it's dolostone. And look at the chemical formula here. It's a calcium magnesium carbonate. Mostly biochemical would be coquina. That is a term for just generically any rock that is composed of fragmented seashells that have been cemented together. Chalk is formed from microscopic shells, microscopic critters called foraminifera or coccolithopers. And oolitic, oh, I always forget, yeah, that's right. Sorry, I'm talking to myself. And oolitic limestone forms from ooids, which are these spherical grains that have been rolled around in carbonate-rich water, and kind of like a pearl would be, but it's not from an oyster or anything that inside of an oyster. They're just grains of sand rolling around on a beach. So this is fossiliferous limestone. You've got no problem seeing the clasts in here. The shells haven't been recrystallized at all. They've just been cemented together. What you're looking at here is a fossilized reef structure, coral reef structure. This is in Texas, and we don't normally think of reefs being common in Texas, and they're not present day. But there used to be an ocean there in geologic time, and these reefs are proof of that. There's a park there called Capitol Reef Park, not to be confused with the one that is in, I think it's in, there's one in Utah, but this one is a different one. It's in Texas. This is fossiliferous limestone again. You can see these shells in here. You can have no problem picking these out. They've been cemented together, and in the southeastern part of the country, coastal Georgia and coastal South Carolina, they use this as a building material from the 1700s on. So you can go there and see these buildings that are constructed out of these blocks of tabby, which is what the local name for it is. What you're looking at here, they are microscopic. You would not be able to see these. They've been magnified. They're called coccolithophores. This is a plankton, lives in the ocean, and this is what the White Cliffs of Dover are made from. White Cliffs of Dover, southern part of England, very extensive, very recognizable. So it's basically chalk. And it's very erodible. You can see here's a landslide into the ocean. This happens all the time with the chalk. Then there are also other organisms that live in the ocean that are composed of calcite too, just like chalk would be, and they're called foraminifera. Most of these critters have different species that live in tropical or subtropical or cool subtropical or subpolar waters, and that's one of the ways that we can determine where that rock formed. We can look at these, that can extract these from the rocks and look at them under magnification, and there are experts in these organisms and they can tell you what sort of temperature water they lived in. And I'm going to skip that for a second. Here's a present day coral reef. And here is a fossilized coral reef. This is a quarry. And you can see the reef structures still in here. These little critters right here are also highly magnified, and they are called radiolarians. Radiolarians are composed of silica, and they're called the snowflakes of the sea because they come in such a variety of shapes. Again, these can be used, if you know the species, they can be used to tell the temperature and chemistry of the seawater. And these form, when these radiolarians in the ocean die, they will fall very slowly to the bottom of the ocean floor, and they eventually will turn into a muddy ooze, a siliceous ooze, because the mud is composed mainly of silica. And when that lithifies, we get a rock called chert. Chert can come in many forms. The quartz crystals from the radiolarian are now going to be microscopic, so you would have to have a microscope to be able to see the structure here. And it comes in, when it's a red color, it is called jasper. Here's some banded jasper here. Agate is also another name that we give to it. Agates can be in many different colors. This happens to be a banded agate here that is also a geode. If it's black, it's flint. So this is flint. The Native Americans used flint to make arrowheads and spear points from. It takes a very sharp edge. And it can also show up as irregular masses in other rocks, like here. Those would be called chert nodules. Where I used to live in Virginia, there's a lot of limestone, and if you're driving down the road, there are all these limestone layers, and you would see these rounded masses in the limestone, and they would be sticking out a little bit further from the limestone because they're made of silica, so they're more resistant to weathering. The limestone is going to weather more quickly, so these kind of protrude out of the limestone. So here comes a little bit of California tectonic history. Here we have an ocean plate, and it's subducting underneath a continental plate. The continental plate here would be North America, and the ocean plate would be the old Farallon plate. So we have those little radiolarian critters that are dying and falling to the bottom of the ocean floor, forming that ooze, along with other rocks that we'll talk about later. But look what happens. They are getting pushed this way toward the continent. Now the continent is not going to be subductive, the continental plate. It's going to be buoyant, kind of like a beach ball. If you ever tried to press a beach ball into the water, it bobs right back up. Well, that's the continental plate. So it acts almost like a plow as these are converging on each other, and it's scooping up these ocean floor rocks. And that is how a continent grows, because these rocks are being accreted onto the edge of the continent. And remember, one of those rocks is chert. This is the world famous ribbon chert in the Marin Headlands. This is part of the Franciscan Formation, which is a famous formation because it's just a mishmash of all these rocks that have been plowed up off the ocean floor. And this has all these contortions in it. It's folded because of the compression between the two plates. If you go to the Marin Headlands, you can see this very clearly. Here's another view of it. Diatoms are also microscopic critters composed of silica. They can live in lakes, they can live in ocean, and when these little critters die, sometimes they can form diatomaceous earth, which is what you're looking at right here. This is a mine where they're mining diatomaceous earth. So silica, mainly silica. This stuff is used, they package this stuff. It can be used for pest control. It can be used in water filtration for swimming pools. You can take it by mouth to be used as a source of silica. If you have high cholesterol, you just have to make sure that you have the food grade diatomaceous earth. It can be used to brush your teeth. People take it to improve their joint and bone health. So a wide variety of things. It can be used as a food supplement for your pets. So lots of uses for this material.